Recorder.
All
Okay.
right.
Welcome everyone to our presentation webinar on radar gas. I am very pleased to introduce you to Colin Tomas. I've heard about Colin's name well before I got into this. I always knew through Rudy and a few other people in Radon Gas that says, well, you need to talk to Colin. Colin should go to. So we reached out to Colin, and I'm very pleased that he's given us a presentation. So Colin's a bit of background. He loves to look at the root causes of building problems using physics and science, which eventually brought him to a long-standing issue on radon gas infiltrations into buildings and homes. He's trained certified risk mitigation professionals across Canada to help radon problems in all kinds of buildings. He's keenly interested in how we can build low energy homes that are comfortable and durable. And he leads an example building net zero homes by building his own family home in Calgary. He's also very involved with the Association for Radon Gas Technicians and Technologists, which we're working with moving forward with this project as well. And he's got a Bachelor's of Science from University of Calgary and a diploma in Object-Oriented Software Technology, also from Calgary. So I'll turn it over to Colin. And I guess, Colin, do you want to just go and as we get questions you address, or at the end, whatever your preference is, let us know.
You know what? If someone's got a pressing question right off the bat, let's do it. And if they want to wait to the end, perfect. Got a lot of slides to go through. So either way works for me.
Okay, over to you.
Awesome. Thank you, guys. Sorry, I lost my webcam for some reason. Maybe it'll pop back here. But you can see my screen for my presentation, right?
That works. Yep.
Awesome. Okay, great. Awesome. Yeah. Okay, great. We're going to talk about some practical building considerations for radon control. You know, a little bit what I do. I fix radon issues primarily and other soil gas issues like perchloroethylene or other types of contaminants in soils in residential, commercial, industrial processes. I do a lot of training for people to become certified to do radon mitigation and just have a lot of fun in this area. It's so interesting, and I hope you find it to be interesting as well. You know, it all started when I built my house. I built a net zero energy house out here by Calgary and looked really safe, but actually I tested and I had high levels of radon. That's the first I heard about radon. And I thought that's impossible. We don't have radon here. Nobody thinks they have radon wherever they are, but radon's widely geographically dispersed, as you guys are probably aware. So yep, any place can have radon. I had radon and I need to fix it. Now, when we think of radon in new construction, I think we're usually thinking about this kind of a thing. A rough-in for most parts of the country, maybe except for BC, would have a stub coming through the ground like this. And how many times have we seen it in an area that wasn't accessible, like under the stairs, and it's far from a decent venting point? That's what we think about. Also, I see a lot of SDR35 pipe being used, which is great below ground, doesn't work so well above ground. We need to transition to a Schedule 40 pipe of some sort. There's a picture of the roof there on the right. I think that might be somewhere near Kelowna, somewhere around that area. And you can see the mitigator had to paint it with some latex paint because SDR.
Oh, my air. Colin, I just muted you by air. Oh, Colin.
Did that work?
Yeah, there we go. Sorry about that.
Okay, now. Now I've got this thing on my screen. Let's see here. I think if I go like that. Okay, there we go. Yeah, so SDR35 pipe is not resistant to UV rays, and therefore we need to paint it with something. And we've painted it here with some latex paint to protect it from the UV rays. We find a lot of, challenging radon rough-ins to activate. You can see here there's a whole bunch of them. They're stuck in the wall. They've got a temporary cap instead of a permanent cap. The one in the middle there behind the sump, you can see it's just barely enough room for a cap sticking on there. They're usually crooked. and there's lots of leaks showing. I'm going to talk about some of these issues and how we can fix them to make an awesome radon rough-in so that future occupants can really protect themselves against this radon gas. Sumps around the country, it's very common to have sumps, and Health Canada did a research project, and they found that in all the new construction they looked at, they never found one sump that was airtight, not one. So sumps, I think, are something we need to look at to make sure we're thinking about the gas that's in the ground and preventing it from getting into the house. But what is radon anyways? I mean, I think most of you guys probably have some idea what radon is, but let me just refresh your memory. It's a gas, and it's a radioactive gas. And you can't see it, you can't smell it, you can't taste it, but it's in the ground and it gets into our houses where it causes a problem. It's a lung cancer issue, and it needs to be dealt with. But how do we measure this gas in our buildings? Well, what's funny about it is we don't actually measure it by parts per million or parts per billion or that kind of way that we're used to measuring contaminants. We actually measure radon by its rate of radioactive decay. And that sounds pretty funny, but radon decomposes in it and it shoots out these high energy alpha particles. These are the things that are causing lung cancer, and we measure how many of those high energy particles are coming off. So it's kind of an interesting thing. We're not actually measuring the gas, we're measuring the high energy particles that are coming off. And one of those radioactive particles coming off per second is called a becquerel. And the Health Canada has an action level of 200 becquerels per cubic meter. So if you could imagine a box 1 meter by 1 meter by 1 meter, when the rate of radioactivity exceeds 200 of these little high energy particles coming off every second, that's when Health Canada says, hey, we recommend you do something about it because this is a serious lung cancer issue. That's how it's measured. So why do we care about it? Well, it's a lung cancer issue, and your risk depends on how much radon you have, of course. And at 800 of these radioactive disintegrations per second, remember Health Canada's action level is 200, but at 800, your risk of dying from this thing is greater than all accidental deaths combined. Car accidents, drowning, electrocution, fires, poisoning, all the accidental stuff you can die from, it's greater than that. So it's actually a big issue. And it leads me to one of the myths, which is that, well, why don't we just test the ground before we build a house? And you can't do that because radon is ubiquitous. It is in the ground almost everywhere, but that doesn't mean it gets into your building. So we want to test the building, unfortunately. If we could just test the ground and say, this spot's bad, don't build a house there. This is a great spot, build a house there. That'd be awesome, but it doesn't work that way. If we tested the ground, we're going to find radon almost everywhere. So we need to test the building, not the ground. Now, you've talked about different types of tests. Well, there's short-term tests, but the issue with short-term tests is that radon is variable. Radon levels change from moment to moment. So you can have a good test and it tells you exactly how much radon it's seeing right now, but come back in a week, maybe that's not the same amount of radon. So we want to do long-term tests, right? Because radon levels change over time. Here's a graph of the hourly radon levels in some building, and we can see here that we had a high of about 1,700, a low of about 300 or so, maybe 200. So if we just tested for an hour, we would get any number between 200 and 1,700, and we wouldn't really know what we're being exposed to. And so Health Canada recommends long-term tests. And Health Canada's definition of a long-term test is one that lasts for 90 days or longer. 90 days to a year would be an ideal long-term test. A lot of people don't want to wait that long, so we say, okay, 3 months in the winter time between October and April would be a viable proxy for a year-long test. So 3 months is generally ideal. Now, if you don't want to wait that long, approved devices. Yeah, there's a number of approved devices, and this is kind of important because not all devices are approved. So for example, this device here, which is a, where's my sweet spot? Oh, right there, okay. This device here is a consumer grade device. Maybe it costs $200 to $250. They're quite accurate actually, but it's not approved. So I couldn't use this test to test your house for radon and tell you it was high and I'm just gonna fix it for you. I couldn't do that. But as a homeowner, pretty darn accurate, and it's useful to have something like this. There's a lot of different types and styles and shapes. This one has no display on it, so you have to actually connect it to your phone, but these ones are very popular. There's other types of devices that have other functions. This one's measuring radon, and it's measuring PM 2.5 for the people who live in smoky areas like any place around British Columbia. But approved devices would generally look kind of boring, like a little puck like that. That's an approved device. Here's another example of an approved device. And they come shipped in these special mylar plastic that is impervious to radon. And as soon as you open this package up, that radon test is started. And you can't put it back in a Ziploc bag to turn the test off. Ziploc bags are transparent to radon. Radon will go right through a bag like that. So once you've taken it out of the bag, it has started the test. You leave it out for 91 days, and then you generally mail it into the lab, and they'll email you back your results. So consumer monitors, I showed you a selection of those. They're really great if you want to test more than one location, because sure, you pay $200 or $250, but you can test downstairs, upstairs, kids' room, neighbor's house, your parents' house, your friend's house. You can test a lot of different places. So they can be actually more economical if you want to test a number of places, but I couldn't use one to charge you money for it. They're not approved. Okay, so why do we get radon in our house anyways? I didn't send an invitation, so why are we getting radon in the building in the first place? Well, this is kind of interesting. This is how we can keep radon out, is we have to understand why it's getting in. And in order to have a radon problem in a building, you need to have 3 factors, and you need all 3. If you only have 2 out of 3, you're not going to have a problem. You have 1 out of 3, not going to have a problem. You need all 3. Unfortunately, most buildings have all 3. And those 3 things are, we need a source of radon. We need a pathway for radon to actually make it into our building. And we need a pressure differential to drive that radon into our building. You need all 3. And most buildings do have all 3. Let's take a look at some of those things. What about the source? Well, take a look at this. I don't know if you can read it, but Canada is number 2 for uranium mining in the world. We're number 2. We have lots of uranium, and radon comes from uranium. Uranium-238 decays and forms another material, and so on until finally radon gas is formed. So radon comes from uranium, and it doesn't take a lot. You don't have to live in an area where they're mining for uranium actively. It's not like that at all. It's very small trace amounts. And you can see in that upper right-hand photograph there that the glaciations we've had in Canada really move and smear all these old mountaintops and stuff. It grinds it up in a powder, takes that uranium ore and materials with it, and disperses it throughout Canada. So most places in Canada have strong likelihood of radon potential. There's a few areas that have less radon than others, but in general, we can find radon every place in Canada. Well, what about pathways? So if we have radon in the ground, okay, that's unfortunate, but it is what it is. What about pathways? Well, any kind of a gap in the cement or in the air barrier surrounding our homes that are around the soil can potentially let radon in. So joints around drains, cracks, sometimes under furnaces or HVAC, there's big holes. Sleeves where we've sleeved the water lines, so the concrete finishers don't nick the water line. He'll put an ABS pipe through the ground. We call it the radon straw. That's where radon streams through. Cinder block walls, penetrations. I mean, you guys can probably think of a lot of different pathways you've seen where radon can actually enter the building. Finally, pressure. You know, air moves from high pressure to low pressure. So in that balloon, air inside that balloon's under pressure. So if I put a hole in that balloon, air would come out. And it's just that simple. That's how radon gets into our buildings. Our buildings are operating at a low pressure relative to the outside air. And so they suck the radon in. Just like this. We call it the thermal stack effect. And anytime it's colder outside than inside our houses, your house is acting like a chimney, warm air inside your house is rising, and air is leaving through the top of our house through building defects around pot lights, ceiling fixtures, attic fans, or attic hatches, and penetrations where plumbing and electrical go through into the ceiling plane. All those places leave little gaps, and this warm, less dense air inside our house takes advantage of those gaps and travels through the top of our house. And all the air that leaves has to be replaced by an equal amount of air that gets sucked in from the bottom. So our houses are just like chimneys. It's a big column going straight up like that. That puts a suction on the ground. So as you can imagine, tall buildings suck harder than short buildings, right? It's a taller chimney. Doesn't mean a tall building is going to have more radon, but it could. And if it does, it's potentially because it's sucking harder on the ground. But of course, there's confounding factors. You know, a shorter building might be bigger. If it's a bungalow, you have a 2,000 square foot bungalow, you have 2,000 square feet in connection with the ground. If you have a 2,000 square foot two-story, you might only have 1,000 square feet in the ground. So there's a lot of what we call confounding factors, factors that are fighting each other to determine whether or not they're increasing radon entry or decreasing it. Now, once it's in the house, coming in through the foundation in the basement, it moves up through the rest of the house, right? A lot of people think it's a basement issue and there's only radon in the basement, nowhere else. But this thermal stack effect is drawing air all the way out, up the house and through the top. So it does a pretty good job of distributing radon throughout the house. Now, if you're in an area like I am that has forced air furnaces, that does a tremendous job of mixing up the air in the house and dispersing radon everywhere. If you're in an area maybe where New Brunswick maybe, or Quebec, where they have electric baseboard convective heating, not so much movement of air through the house from that HVAC system. So we might find bigger differences between the radon levels from floor to floor. But typically I might only find around here a 15% difference. So if we had 800 becquerels in the basement, you know, we might find 720 on the next floor and, you know, 650 on the floor above that. Pretty similar, pretty similar. Now, our houses also can increase this, not thermal stack effect, but just through simple mechanical ventilation. Like what happens if we bring in outside air? Here we've got an air handler that's connected to the furnace. The furnace runs. We're not exhausting any air out the house. We're just pulling it in. Well, in that case, we're going to pressurize this house a little bit, a minuscule amount. And if I exaggerate it, we might pressurize the house and that might push radon back into the ground. So that would actually help reduce radon in that case. Now, what happens if we turn on all our exhaust fans, kitchen fans, attic fan? What's going to happen then? Well, if we depressurize the house, we might cause more radon to get sucked in through the bottom. It might increase radon entry, might have more radon. More likely, we're going to have something like this. We're going to have some number of exhaust fans on, and we're going to have our furnace on. So what do you think is going to happen? What do you think is going to happen then? Is the radon going to increase or decrease? Does anyone have any ideas? Can you guys still hear me?
Oh yeah, we can.
Well, assume you guys are still there. What's going to happen? We don't know. That's the whole point. Radon could increase or radon could decrease. We don't actually know because we're fighting. Is there going to be more air coming in or more air going out? I'm not sure.
But what if you open a window? So you talk about the fans. So what, say, rather than fans, but you have a window in the upstairs?
Here's a video showing this thermal stack effect. Let's see if it'll start. So what happened there is I opened the basement door to relieve the thermal stack effect in the house, and that bag inflated. That's soil gas. That's got a lot of radon in it. See how fast it inflated? How many cubic feet of air they had in there in no time? And then when I opened the door, I killed the suction of the house, and the radon fan was able to depressurize it and pull that bag down and deflate it and depressurize the slab. But with the door closed, the house sucks on the ground stronger than I can. Are you guys still there? Can you still hear me?
Oh yeah.
Yes.
Maybe I should log in again. Make sure you guys are still there.
Colin, we can hear you.
Unless you're all muted.
Nope. Yeah, Colin, we can hear you.
This is showing that the house actually is sucking on the ground and radon is moving from the ground into the house.
Colin, we can hear you.
With the radon system installed, the house becomes pressurized relative to the ground and we can collect radon. I'm going to make sure I'm still on here.
We can hear you.
Oh, can you guys hear me on my normal presentation?
Yeah, I can
Okay.
hear you.
We can.
Okay, must be my speaker. I'm going to disconnect from here.
Yeah, we can hear you, Colin. You're scaring the bejesus out of us.
Okay, here we go. Closing this one out. Okay, sorry. I can't hear through my speaker for some reason, must have timed out.
All
So I
right.
think I'm talking to myself. So I'm glad you guys are still there. Thank goodness. Okay, I'll just continue on, but I won't be able to hear you. And then at the end, I'll figure out a way to make this work again. Yeah, so this is what a radon system is doing. It's actually drawing air out of the ground, which creates a small negative pressure. And therefore, radon gets the house air is at a higher pressure than the ground air, and it pushes down the ground, keeps radon out. So we're not exhausting radon. We're not depleting the amount of radon. Radon system is not depleting the amount of radon that's coming into a building. That's actually impossible because for any radioactive material, the rate of depletion is dependent on the parent product with the longest half-life. And unfortunately for us, with radon-222, the parent with the longest half-life is uranium-238, and it has a half-life of 4.5 billion years. Billion years. So it would take 4.5 billion years to remove half of the radon. And that's not going to happen. So it's being constantly brought in, and we need to change the pressure under the ground in order to fix the radon problem. Yeah, so my dream house, and maybe Rudy would attest to this, a simple up and out system with clean, coarse gravel. The slab is sealed perfectly. It's an unfinished basement, so I can seal all the cracks, a big mechanical room, and a puppy to play with. That would be an ideal mitigation house to work on. But they never exist. So we see all kinds of crazy stuff in the field. Let's take a look at some of the things. Well, one thing I want to mention is a radon rough-in, which is the standard for most places across Canada, except for maybe British Columbia, which sort of has, they don't want to call it a passive system, but it's often called a passive system, more correctly termed an extended rough-in. But for most places across Canada, they have a rough-in, which is just a pipe sticking through the ground with a cap on it. That's not a radon system any more than the bathroom rough-in is a bathtub. And this poor guy here is going down to his basement to have a bath, but he's only got a bathtub rough-in, so he can't have a bath. Same thing with the radon system. Radon rough-in system is not a radon system and won't decrease the radon. Well, here's something I see all the time, especially in British Columbia. For some reason, you guys love strip footings. We don't see them very often in Alberta. Strip footings are these continuous foundation elements that are underneath the slab that are used to support load-bearing walls or beams or whatever. And instead of using teleposts, they use a continuous strip footing. That's a problem because we need to depressurize the entire building and we don't know where the radon's coming from. It could be coming from any part of that house. So we need to suck somewhere and draw air from underneath the entire gravel slab and pull it over to our radon system to change that negative pressure. And strip footings would get in the way. So if I'm in this building and I've got these 5 areas separated by strip footings, how do I know where the radon's coming from? I can treat area 1, maybe that's where the rough-in is, but if I depressurize that portion of the foundation, it may have no effect on sections 2, 3, 4, and 5. So I may not have fixed the radon at all. So strip footings are a problem. So what can we do? Well, we can put jumpers through. Same way they've got a little jumper through this wall, that footing there to move that, bring that water pipe in. That's one solution. It's not always even obvious if there is a strip footing at the time that I'm working on it, when the building is completed. So I don't know. So I rely on you guys to put sleeves into these areas or do some other techniques so that air can be pulled from the entire slab. Here's a doorway, and I was fixing this building and I measured a pressure on either side. So you can see my manometer there is measuring two different pressures. It's a dual channel manometer. And on one side of that doorway, I got negative, what does that say, 74 pascals? And on the other side of the doorway, I got negative 2 point something pascals. A big difference. Those are still good numbers. We can still fix the radon, but it just shows you there's something in the middle. There's a barrier that's changing the pressure underneath the slab on either side. In this case, a strip footing through a doorway is probably what I suspected. Is this a strip footing? So here we got a beam. I see a couple metal teleposts. I see a portion of a wall. No, we wouldn't see it. This wouldn't be a strip footing because we see a telepost. So most likely there's just a simple pad footing underneath those teleposts and open gravel in between those areas. So we could depressurize this foundation without doing anything special. So teleposts are our friend. Sometimes we have to be a strip footing detective. I fixed this house at a time it was undergoing some renovations. And look what they did. There's a steel eye joist right there. That's pretty peculiar, isn't it? And I wondered, is there a strip footing running underneath where this wall used to be? And sure enough, if you look closely on the right-hand picture on the insert there, that's a photo of the bottom of the metal telepost supporting that one end of that eye joist. And you can see the base plate for that telepost is above the slab. So it was added in after, right? That's telling us it was added in afterwards. So that beam has been added after. And most likely that house used to have a strip footing running all the way down, a load-bearing wall all the way around. And we have to deal with that when we mitigate. More clues, sometimes under these walls, they put a little bit of a stub wall, sort of. And you can see where there's a little bit of a concrete curb there, about 1.5 inches high. That's a problem. And that tells us, hey, you've got a strip footing underneath there. Another clue is it's a 2x6 wall. You don't see a lot of 2x6 interior walls because they take up too much space, right? You do a 2x4 wall. So if you're doing 2x6, you may have a load-bearing wall. So I have to look for clues like that. And so we rely on builders to accommodate strip footings at the time of construction. This would be an old house, of course. This would be 1970s or something. But when you build a new house, we need to have some way of getting the pressure to travel from one side of the footing to the other. Sometimes it can be obvious that there's a strip footing and sometimes not so obvious. So on the left-hand side, that's pretty obvious. We can see where they actually jackhammered a concrete wall to get to the other side of it. So yeah, there's almost for sure a strip footing underneath that concrete wall. It's probably a load-bearing wall for sure. Not so obvious, middle picture, you can see where there's some disturbance in the concrete. It looks a little bit like it's changed. There's a little bit of texture difference in that one. And so that looks, I'd suspect there'd be one there. On the right-hand side, that's completely hidden. The floor's been painted, so I don't see any textural differences where the strip footing used to be. And it looks like I'm just sucking from 2 points 2 feet apart, but actually I'm sucking on either side of a strip footing there in order to reach the entire foundation. What about stairwells? Quite often, there'll be a strip footing of some sort under stairwells, but they're not too much of a problem typically because they don't extend across the entire foundation, so the air can go around them. So stairwell footings tend to be fairly isolated and limited in scope. So stairwell footings are generally okay. Crawl spaces, of course, they could have strip footings as well. Here we are sucking on either side of a strip footing to depressurize a membrane in a job. So what can you do? Well, you could install one radon stack for every closed section of foundation. You could install sleeves through the footing so the air can move across the footings. You could run perforated pipe or tile in a loop that connects each section, just go right through all the sections. All those things would be great tricks that would really help the mitigator and help the homeowner to be able to control the radon with a single radon suction point. That'd be great. What about hanging walls? Maybe at the end you guys can tell me if you guys see this a lot, but I see it an awful lot, where the wall was actually installed before the concrete slab was installed. That's what I'm talking about. And we see that all the time. So here's what they normally do. So normally you see we've got our concrete wall, we've got our footing, we've got our gravel. Well, they'll put their slab, gets poured first, right up against that concrete wall. And then they installed their frost walls, right? With their insulated walls. It's sort of just for energy use. It's just to hold up the drywall and the insulation. It's not a structural component. That's what normally happens, right? Well, here's what happens sometimes. And a gap, of course, forms back there. That's a problem, but generally we can seal it if you haven't sealed it at the time of construction. Okay, here's what sometimes happens. Uh-oh, wait, look, they put the wall first. The wall came first. Well, how did they do the floor then? There we go, the floor came second. But you see that gap in the back there? That's because the concrete guys didn't push the concrete all the way under that wall. So we get a much bigger gap in that area, a big gap, and it can cause a big problem. And when we're trying to depressurize that gravel layer under the slab, that gap can be unmanageable. So why would that happen? Well, here's what I really want to know from you guys at the end of the presentation. Why does that happen? This is why I think it happens. I think it's Friday and they can't get concrete on the weekend, but they want to keep the framers busy. So they tell them to hang those walls, and on Monday they bring the concrete and put it in afterwards. I think that's the scenario. Someone make a note of this and let me know if that's really what happens. I gotta know. I gotta know. So this is what it looks like to a mitigator. Look, I've taken out a section of that wall and look at the size of that gap. So don't kid yourself. The concrete guys are not pushing the concrete underneath that wall at all. They're just making it look good. It's just getting to the edge of the wall, and then that's it. And we have a big gap. And a big gap like that is a tremendous leak for radon to come into the building. And when we try and depressurize that gravel, it's a tremendous leak for our radon system to suck air back down. So that gap is really big, and it's a problem. And when they do it around the entire house, it can be unmanageable. There's a close-up there. That's an awful big gap. So clues that I look for is things like this, where I can tell that the poly or the concrete has been poured up against those lower plate of that wall. If I see concrete poured up against that bottom plate, I know that wall is hanging. Right there, another picture. I can see that concrete has been poured up against the poly, and I can see there's a little bit of a gap there. That's a sign of a hanging wall. How about this wall? I don't know. It doesn't. No, I don't think so. No, that concrete floor extends underneath that base plate of that 2x4 wall. That is not a hanging wall. So what can you do? Well, you can try and get the concrete guys to push the concrete under the hanging walls all the way around. I don't know if they're going to listen to you, but you could try that. You could come in after and seal that big gap with concrete or spray foam. I've never seen anyone do that, but that'd be great because that's what I have to do. And maybe we have to cut the walls around the entire lower part of the walls in the entire basement in order to do that. And so it'd be much easier to do that at time of construction. And of course, the building code says, hey, we need an air barrier around the entire envelope of the house. And it's questionable if we have an effective air barrier if we have a big gap all the way around. Concrete shrinkage. Well, we all know there's two kinds of concrete. Concrete that is shrunk and concrete that will shrink. So we can't get away from concrete shrinkage, but we can mitigate some of the impacts, right? So this is the floor probably in Home Depot or Costco, and you can see that there's a control joint there. They filled it with caulking. They didn't do it the proper way, and the concrete is shrunk and it's pulled away from the caulking. And concrete shrinkage is important. We can deal with it, but because it's predictable, but it will happen, and it's very powerful. So here's a close-up of that same floor, and we can see that the concrete is shrunk, and in this control joint, it is pulled away from the walls, and we have adhesive failure. That means that the concrete is pulled off the wall. Here we see a floor-to-wall joint. This is what we see in a house, and they tried to caulk the perimeter, as is in the latest National Building Code, but we can see it's failed. And this is called cohesive failure because the caulking failed. It stays stuck to the wall and it stayed stuck to the floor, so it's not adhesive failure, but the caulking itself has split. So that's cohesive failure. There's a close-up of it. And it doesn't take much. A little crack like that, and we could have a radon problem in the whole house. So that's just a 1 foot section of that caulking I'm looking at. And you might say, well, it's mostly sealed, but that's the size of the gap that you need to create a radon problem in the entire house. So that's not good. There's adhesive failure. It's pulled off the wall. And then when I cut a piece of that caulking out just to see what was underneath, I could see that the slab had shrunk about 1/8 of an inch. and caulking cannot stretch when it was applied like this, and so it splits and it cracks and it pulls off the wall. It's normal. I see it 100% of the time. I've actually never seen a wall that was sealed stay sealed for the duration of the building. After 1 year, the concrete shrinks enough, it pulls it off the wall every time. Now, we can anticipate that actually, and this is a little excerpt from Dow Corning's America's Technical Manual, and they say, you know, in that pour joint design there's no backer rod, the joint is the wrong material, and it's the wrong shape of a joint, and it says, hey, I've circled there, there's no bond break material, therefore the joint will not accept movement. And this is a big myth. You know, a lot of people think that because I'm using an elastomeric type of material, something that's stretchy, that's all I have to do, and if I put a stretchy material there, that it will move with the building. But actually, no, you need to have a bond break there. You need to have a little piece of material that's not part of the wall, that the caulking won't stick to, that allows the caulking to stretch. So that's why in this diagram, on the left-hand side, you see the good joint design. There's actually, it's hard to see, but there's a little triangular backer rod in the corner of the joint. That caulking can't stick to that, so it can only stick to the floor and the wall. And then as the floor and the wall move apart, that caulking now can stretch. It works. But when it's stuck the whole way into the corner, there's no part of that joint that can stretch. So it pulls apart every time. Now, this is a data sheet from Tremco, and they do show how you can create movement. And they got some backer rod in these control joints in such a way that they prevent double-sided adhesion and allow movement. So there's a way to do it. It's a little bit complicated, but there's a way to do it. And we're currently dealing with this in the latest building code updates. We're trying to figure out how we can make something work. Shape is critical. Has to stretch, right? So we need a thin part. If we only have a thick, big gob of caulking, for sure that can't stretch. It's too thick. It's like grabbing either end of a big fat eraser and pulling it, and you can't hardly get any movement. But if you took a razor blade and you shaved that eraser down so it's got a thin part in the middle, yeah, now you can actually stretch it. So we need a thin part in our joint. A big fat gob isn't going to allow any movement. So the shape is even important. So what can we do? Well, we can anticipate that the concrete is going to be shrinking. We know that 100%. And in a commercial job, we might rebar the slab edge to the walls, and we might saw cut the slab, and we allow for movement that way. That's what they do in a commercial job. But I don't see any saw cutting happening on residential jobs. So maybe we could caulk the joint in a way that will accept movement with a bond break. And if you guys are interested, we could talk about some ways I've been thinking of to do that super easily and cheaply and fast. And then we can accommodate that movement and make it so much easier for your radon mitigator. This one's a huge issue that we see all the time, plugged rough-in pipes. And plugged rough-in pipes, this would be the portion of pipe that's underground in the gravel. And it's in the gravel, right? And we're going to show some pictures from the building code that there's no showing you that it's wrong, but what happens is you put your pipe in the gravel and you cover it with gravel. Gravel goes in the end of the pipe and you plug it off and it doesn't work. So it's like sucking on a milkshake and there's a big blueberry stuck on the end of your straw. That's what's happening to the radon guy. He applies depressurization equipment to your rough-in, sucks on that pipe, and the end of that pipe is covered in gravel and there's no air movement. You can't fix it. So it's a big deal. The building code talks about having an inlet and outlet, and it talks about the type of pipe and how it all works. It has some pictures in the appendix, but in all cases, it just shows this pipe in the gravel where it can be plugged. And so I would say about 50% of the rough-ins that I activate are plugged and can't be used. It can't be salvaged. So we might actually abandon them. That's generally how we would deal with it. Or take a look at this. If you look in the back behind that water heater, you see how I tucked a radon fan up in the back there behind the water heater? Yeah, so that goes to a rough-in. And if you look in the foreground, can you see that patch of concrete here that's near the front, that circular thing? It's a darker patch of concrete. Okay, I located the end of where that rough-in went to, and I cored a hole through the slab, and I found the end of that rough-in pipe in the gravel, and it was plugged, and I reached in, and I pulled the gravel out from the end, and then I patched the concrete again, And now I could add my depressurization equipment and activate that system in a way that made it work. But if it wasn't plugged in the first place, way better, right? Way better. So what we can do with that is some radon cages under the slab. This is what we'd use for commercial buildings, and it's not in the building code for residential, but if you could think of some way you could do something similar for residential, you would be a genius, because we really need to be doing this on all buildings in order to reduce that pressure. So let's see here. Yeah, here's an example of a cage that we'd use in a commercial building. This is a small one. It's 6 inches tall, about 18 inches in diameter. It's galvanized with a mesh here, and there's a pipe stub here. This is where we would put the end of the rough in. So we just terminate it like that, just like that. And now the end of the pipe can't get plugged, and we've got this mesh holding back the gravel. So all the gravel piles up around here, but it doesn't pile up in the end of the pipe. And all those little cracks between the gravel add up to a significant amount when we look at the surface area, and it really lowers the pressure drop. And we can fix a school, with just a couple small cages. But if we just buried this in the gravel and it was plugged in that with gravel, we can't even fix a small house. So this is something that you could maybe think of in your own construction sites. A loop of weeping tile might work. Cages are ideal, but weeping tile might work, or something else to exclude gravel from the end. Just having a screen on the end isn't quite enough, because the gravel's still too obstructionist. We've got to hold that gravel back and create a little bit of a surface area void here. That would be best. So what could you do? You could put a cage on the end. You could use weeping tile, perforated pipe. That would go a long ways. Oh, great. Awesome. I raced through that because we had so many slides and I wanted to get to your questions. So since I can't hear you, I have got to do one of two things. I've got to either activate my speakers, or what I think I'm going to do, I'm just going to dial in again, because we saw how fast that was, and I will undial in what I'm doing right now. So if you could look for me. Oh, wait, now I can hear you again.
Oh, there you go.
Awesome. Oh, great. I'm glad I can hear you now.
All right.
All right. Now that was a whirlwind. That was a whirlwind tour there, but I wanted to get through a bunch of material, and hope you found something there that was of interest to you. And I want to get directly to your questions. What kind of questions have you guys got for me? Oh, can anyone tell me about that hanging wall? Why is that happening?
Economics.
Yeah, but why? What do you mean economics? They're still doing the floor, they're still doing the walls. Is it, like I said, they're waiting for the concrete and they need to get some work done because concrete's delayed?
I'll throw that out to people. That'd be my assumption, but I'll throw that out.
Okay. Yeah, I'd like to know that for sure.
Okay, anybody, any questions? You can throw your hand up through a chat or just turn on your video.
Excuse me. Yeah.
Okay, I'll start. I have a bunch of questions. So,
Great.
Colin, what do you do in First Nations that don't have access to gravel? Which is like Saskatchewan, sandy soils.
Yeah.
I think Manitoba as well. I believe certain parts of Alberta. Like you can bring in gravel, but it's extremely, extremely expensive. And we ran into this discussion on weeping tile and French drains and where the code requires gravel. So how do you respond to where gravel's not possible or too expensive? Like do you buy ground up rubber tires? I don't know what the alternative is, but
Yeah. Well, it's a great question. I wouldn't have an awesome answer for you other than the building code talks about gravel. It's got a fairly wide latitude for what kind of gravel. And it says you need to put coarse, clean aggregate having no more than 10% pass a 4 mm sieve. So it's really talking about larger pieces of gravel, not sand, and that they're coarse, so they're big, they're clean, so it's not dirty, and they have to be bigger than 4 mm. That's the definition, and you could drive a bus through that definition. So if you didn't use that definition for the building code gravel, then I guess you're not kind of compliant with the building code. So you may want to go a different approach and have an engineer sign off on a different approach. And from the perspective of radon, we love gravel because we can depressurize that slab easily and we can fix the radon problem. But gravel is used for other things. It's also a capillary break. You know, if you just piled sand, tight sand or silt below a slab, and then moisture that accumulates in the ground will get sucked through that silt and sand. And if you don't have a vapor barrier, of course, it will go right into the concrete, and the moisture goes up through the concrete, evaporates to the surface. And what do we see? Efflorescence, spalling, and deterioration of the surface finish. We've all seen buildings like that. And that's because they didn't have a capillary break. So gravel's not just for radon, it's also for a capillary break to prevent moisture issues like that in houses. From a radon guy, I mean, I wouldn't tell anyone not to follow the building code definition of gravel, but from a radon guy, we want something that can breathe a little bit. If we had to use sand, you mentioned French drain. If you're thinking what I'm thinking of, a loop of weeping tile goes around the entire building that's in a little bit of a trench that has some additional permeable material, gravel or stones or something that's kind of bigger. And then the rest of it was sand, silt, or clay. Wouldn't meet the building code, but those houses like that are built all the time in the States. And they have a ASTM standard for these trenches that contain permeable material, even though the rest of the slab is non-permeable. So it can still work. It may not be compliant with the building code. I know people are experimenting with polystyrene beads. So they're as a substitute for gravel. So they're very lightweight. So maybe it is still hard to get gravel, but you get a big gravel truck, he's usually restricted by weight, not by volume. So if the gravel weighed nothing, if it was little tiny little beads, maybe a giant truck could do several houses because you wouldn't be limited by weight. So there's going to be some other alternative methods like that. There's also styrofoam panels that have little feet on them that form that void space. But then again, you'd have to truck in the insulation panels and you'd have to want to put insulation below your slab, which is a great idea, but isn't common either. So I don't know. I think you'd have to at least do some weeping tile if you want to have a chance to fix that radon problem in the building. Maybe go overboard, 2 loops of weeping tile, you know, something more significant than that. Because when we draw from an area that has low permeability, the draw doesn't go that far. I can't measure my pressure more than 10 feet away. So we'd want a loop of weeping tile every within 10 feet of each other in order to fill in the whole surface. So I don't have a great solution for you, but that sounds like a good opportunity. We need to find a way to make gravel out of materials that are available on site, ball them together and bond them somehow, little concrete beads. I'm not sure. I don't have a good answer for you.
Susan, did you want to elaborate on your question, if you can hear me?
Hi there. Mine wasn't really a question. It was an answer. Just sort of
Great.
speculating on why they're making that void or leaving that void under the break walls. Like, I think maybe they're just not thinking of the radon at all. Like, I don't know that they're trained up on that properly. I think it's a big enough issue that if they knew, they wouldn't be doing that.
Well, if it was easier to build a house like that, I think we'd see that all the time. But it's very rare. That leads me to believe it's something that's, I don't say a mistake, but an alternative pathway. We rarely see it. It'd be far easier to build your walls on top of the slab for sure.
Mm-hmm.
And so if you're building walls without a slab, it sounds to me like a timing issue. They're waiting for, but cheaper, could be. I'll consider that. Yeah, maybe you're right. Who knows? I wish they'd stop doing it though. Luckily, it's only about 2% of the time.
Okay, that's good to know. It made me a little nervous seeing that piece.
Yeah. And it's not obvious. The homeowner would never know. Building inspector no one would ever know except the poor radon guy who knows immediately when something's leaking because maybe he's injecting smoke in the ground and he's seeing a large volume of smoke coming up. He's identifying where the leakage points are, or he's measuring his pressure and he's not getting the pressure response he's expecting. So the poor radon guy finds all these things that are kind of hidden from everyone else.
Thank goodness for the poor radon guy.
Yep, there you go.
Claude here. I have a question regarding crawl spaces in basements. Ventilated crawl spaces, would that suffice as a potential remediation for possible radon?
Usually not. I don't think it's best practice anymore, especially if you're talking about direct ventilating from the outside. And I think the
Yes.
problem comes down to mold. Because now in Alberta, maybe I'd get away with it because it's super dry here all the time, super dry. It's like a desert, right? Or Kamloops. But a lot of the other parts of the country aren't. So if you're in Ontario and it's super humid, you're around Toronto, you've got this cool, dark space underneath your crawl space and you ventilate it. The warm, humid air on the outside ventilates into the crawl space. The relative humidity hits 100%. We get condensation on all the beams and stuff. And I've seen some or heard of some nightmare scenarios where the entire crawl space is a big mold, furry mold ball because of ventilating to the outside. And so I think it's very climate specific where you might be able to get away with that technique, and it would have to be a place where humidity is no issue at any time and you want to keep an eye on it. So I wouldn't do it myself. You could think, I guess, of an HRV. Maybe you create some balanced ventilation because you bring that cold area or that warm, humid area in. We could get some condensation happening in the HRV, which we could ventilate outside. Maybe, but for the most part, ventilating crawl spaces is a mold issue that you want to watch for. So we generally would come in, lay a membrane down, attach it to the sides of the wall, and put an extraction fan that ventilates underneath the membrane, and they're super effective because there's no leaks in the membranes, one solid sheet of plastic. So they work really well. But to your point, sometimes access is an issue. And if you have a really short crawl space that you can't physically get into, those are really problematic. You know, they really are.
Thank you.
No good answer. But ventilating to the outside, be very careful about mold.
Okay.
Colin, it's Rudy here. What
Good,
about
Rudy?
what about injection foam in crawl spaces like of that nature? What's your thought on that, and and what is the type of foams we're using?
Yeah. Now, are you talking about encapsulating the ground?
Yeah, as you know, very tight
Instead of
crawl
a membrane.
spaces to get in, to hard to work in. You know, what's your thoughts on that?
Well, okay. There's two things. One is foam. There's a couple manufacturers of foam that have certified their foam to be equal to a vapor barrier and a diffusion barrier for radon. So you want to first, before you get foam, ask the manufacturer if they've been certified as a diffusion barrier for radon. Some of them have now. There's a selection of them. That's number one. Number two, it would work excellent, I think, instead of a crawl space membrane. But the second thing you said was when access was difficult. And I've had a lot of problems getting any spray foam guys to even call me back. And if I pointed them to a crawl space that had this much space, I don't think they can do it. It's bad enough for you and me crawling around with our respirators on in this dark, spider-filled crawl space, rolling around, trying to spread this membrane. It's very difficult to work, right? Well, could you imagine if you're spraying a material that's dangerous for your life and it's flammable and you're in this very tight space and the gun is normally shooting, 2 feet away and they only have 1 foot of space? I think they have problems with a tight crawl. So I think if we're going to use spray foam, I think it's going to have to be in a crawl space that has a lot more height. So I don't think it's going to solve the problem of the inaccessible crawl spaces. And I've had a heck of a time getting any spray foam guy to even call me back. And then don't forget that spray foam is flammable. It has a flame spread rating greater than 150, so it can't be left exposed in an accessible crawl space. So either that crawl space has to be inaccessible. I mean, you can have a cover, that's screwed on, and sure, you can go in there sometimes, but not a door, not with a refrigerator in there, not with equipment in there. So you either have to make it inaccessible or you have to cover that foam with a thermal barrier, which could be an intumescent paint, which probably costs as much as a spray foam. It could be that cellulose product that I hate. It's all dusty. It could be something else, but you have to keep in mind there's a requirement for a thermal barrier on spray foam that is accessible.
Great. Thanks for that.
Just looking at the time here.
Yeah.
If there's no other questions, I th I think what we're due, Colin, is like that's a fantastic intro. Scared the bejesus out of me. I'm sitting right beside. I have two sub pumps in my house. An older one that's not sealed. It's the older one. One that is sort of thinks it's sealed, but I know it's not. So I'm gonna hurry and buy one of those radons just to see what my exposure is, because that's my main. My house is also 1928, and I'm on a clay base, really heavy clay. As a matter of fact, they use it for pottery, the clay that came out from my place.
Cool.
So
That's cool. Well, sumps are a problem because they have a distribution system or a collection system to collect groundwater, which is typically a perforated pipe that maybe not 1928, or maybe it's a clay pipe, or maybe it's non-existent, but most sumps would have a collection system that'd be perforated that would travel around the entire foundation of the house, designed to collect water from all parts of the foundation and funnel it in to this central sump inside the building. But that's also an awesome radon collector. So sumps are an important radon collector, and they need to be treated. They need to be made airtight. In many cases, we can depressurize the sump system and fix radon in buildings that are otherwise non-fixable, especially in buildings like yours, because you said you have pottery clay everywhere else. Pottery clay is not, air doesn't move through it. So if air doesn't move through it, radon's not going to move through it. So in your case, if you have high radon, it could very well be that either the sump system is responsible for bringing the radon into your house, since you've got this nice easy pathway, or it's where the utilities maybe are entering from the street. They may have bedded that in pea gravel, and it may be a preferential entry point at that location as well. So yeah, you're smart to cover that sump, and you're smart to get a radon detector. Just don't put your radon detector in the sump, because you'll freak yourself out, because it will read thousands and thousands of becquerels, but that's not necessarily how much radon you have in the house. So when you test for radon, put it in a place that you're breathing. Don't put it in the sump, you'll just scare yourself.
Basically right beside me, because where that picture is behind me is a closet, the subs in that room. So I think what we're due is I will follow up with Colin to have one definitely on mitigation, because I have a bunch of questions, but I want to save them for the mitigation. Yeah, this one actually I'm looking at buying from Amazon. I think it's $200. When I was talking to the association, they were actually testing some of these, but I think the one in the middle, Amazon has that one for $200.
Yeah, actually, I love this one. It's one of the early ones, and it's a workhorse. It's so reliable. It's made in Norway. It's not fancy. Gives us a long-term average, a one-day average, and then it'll switch to a 7-day. You saw it went to a 7-day, and you can see my radon's nice. See 11 becquerels for 7 days, 18 for 1 day, 17 long. These are excellent numbers. Health Canada says recommends below 200. Yeah, that's a good choice.
Yeah, okay.
Doesn't connect to your phone, doesn't store the data. You have to look at the screen. It's a workhorse. It really works well.
Okay. Any other questions? Because I know we're definitely have Colin in the fall, which I will actually call. I'll give you a call on the phone to go through my schedule. So, all right.
Yeah, we can talk about mitigation. That'd be awesome. That's my bread and butter. That's the interesting part. I just wanted to give you guys a preview what radon is and how common building techniques can be used to help us fix radon, or they can make it harder for us to fix radon. It goes both ways. So that's a great topic.
Oh, fantastic. And the reason I'm saying that is FNNBOA, we received funding for the Indigenous Building Knowledge Exchange, where basically if you're about to build a home and have a challenge in terms of writing procurements or understanding technical specifications, or most importantly, if you have radon gas, we will look at your plans for free. We will hire somebody to look at those plans to ensure that there is risk mitigation in those areas where there's high radon gas. Now, those areas, Health Canada has a map. I know that Colin showed it. So there's a number of studies that show high areas but we'll be working with those First Nations in many of those high areas and most definitely trying to do plan reviews. So we're in the process of setting that up, but I thought I mentioned to it now because we may have some people on the webinar who are in high radon gas areas. And if you're about to build, it's important to reach out to us because we'd be interested to look at your plans, not only for risk mitigation, but technical specifications, make sure the drawings are up to date and all those niceties of having a third-party review. And again, it's for free because we want to make sure the home is being built to code, at least your specifications are pushing that direction. So on that note,
That's a great service. That's an awesome service. I hope you get a lot of uptake on that. That's going to save a lot of radon issues in buildings, protect a lot of people. I hope you get a lot of uptake on that.
I hope so. And the other one we have actually is the 2000 program as well. So people who are building, we can look at in terms of insulation as well. So that's the other part. So I'll be sending an email out to everybody. I know that our floodgates will open, so we're doing it as a pilot, somewhat of a first come, first serve. But I definitely know the floodgates will open because we identify that as a major issue for most of the communities. They just don't have the expert capacity. And so we can provide that. So, Colin, you scared the bejesus out of me. I'm going to order my radon gas. I'm sure other people in these areas have this issue already. So,
Well, don't be scared. Don't be scared. We never want to scare people. That's not our thing. We want to educate people. This is a problem, but it's fixable. It's totally fixable. So don't be scared, but test. And if it's high, we can fix it. And maybe this mitigation course can help you come up with a strategy to either fix it yourself or hire a professional. Either way, knowledge is power, and it's just science. We can fix this stuff.
All right. Thanks, everyone. And we have our last webinar. Again, we started late because of funding. We have one on plan sign-offs, which is actually important as well. And I will follow up with Colin after the call to slot you in for mitigation, part 1, part 2, possibly. I don't know, but we'll talk how much time you want. Anyway, thanks, Colin. Thanks, everyone. And we'll see you on Thursday.
Great. Thanks.